Hey, good morning, everyone. Chris here, getting ready to have what I think is going to be a pretty exciting episode. So I wanted to get this out there. I worked it through a lot. I had some extra time. I had originally planned to air this yesterday, but obviously that was not going to happen. So seems like we're in a place where I can get this information out today. So I wanted to come back again with episode 6. And I mean, episode 6 is, when I think of like a series, I think of this as kind of like where things are really starting to gel. And I wanted to tease it a little more specifically, but the hashtag put a fork in it should really kind of give it there. And I'm going to introduce some concepts that I think they resonate well. I've gone over them with 2 or 3 people, and it seems to make sense. They like that mental model really works. So just to kind of go back to the beginning and recap the season, we've put together a sample that models the fast food restaurant, and the whole season has been about, orchestration of business processes, choreography, how these things fit together and how they work. And as one of the inspirations for the episode, I had used Jimmy Bogart's talk on microservice communications patterns, but really just communications patterns. How do we make these larger systems work? A lot of the samples around MassTransit focus on a particular capability or a particular feature or the way a particular thing works to kind of show it in the small without a lot of noise around it. And I think what we've seen is if those samples grow, they get really complex, and that creates a lot of headspace that people just don't want to deal with. So far on this season with the fork joint sample, we've gone from simple request response consumers to breaking that out to where the consumer was replaced with a routing slip, to where we had a routing slip that was then tracked by a saga. And we've really kind of adapted the sample as we realized that we need to support some of these choreography and some of these patterns. Things like compensation. If we don't have lettuce for the burger, we can compensate that and fault that particular part of the order. And all of this has been kind of leading to, we've been using the tools in the MassTransit toolbox. We've been using, we've introduced a state machine with the burger state machine. We're using Courier with the routing slips for the different activities. And we've been doing this all within sort of building out this API to support this fast food restaurant concept. And as things started to evolve and we looked at the mental model that we needed to have in place, a concept really started to resonate. And I haven't seen this a whole lot yet. When I talk to other people in the industry and kind of how they're doing things, I'm reminded of some of the old capabilities that we had in previous systems, and I'm reminded of some of the concepts that have really latched on with developers since just even the last few years. The task parallel library in .NET was huge. It was hard to grok for a lot of people, but once they threw async and await in there, it was like, oh, this makes so much sense. It's logically easy to reason about. Every other language has pretty much picked up on it. They've all adapted from if you think about early, and I'm going to use the term futures, because we've mentioned that a lot in this season. But when you think about a future in the early days of JavaScript, it was like you had a dot then and a dot error, and it was all about continuation passing style. And async await introduced that underlying state machine in the method that would manage all of those continuations for you so that you didn't have to think about it. And it's been optimized over the years to where it's super fast, and it's just now async and await is fairly ubiquitous in any modern C# application. So much so that I think it's the envy of a lot of languages to have that capability. But yeah, we still have to distribute our applications, and async and await are great when you're using an HTTP client and you're able to do other things waiting for the response and you aren't blocking ASP.NET and it scales better. All of those things make sense, but how do we apply those to the different patterns in a distributed application, particularly when it comes into messaging? And so the thing that kept resonating with me, at least, and from the people I've spoken to, it makes sense, is this concept of a future. And when you think about a future in the .NET sense, it's the task of T. It's I'm being promised, and a promise is another kind of word for a future, but it's like, I intend to deliver at some point in time some value of T. And you can throw monad out here, you can throw whatever you want. But once that task of T is resolved, it is then complete. And once a task is completed, it can't be uncompleted. It's already done. So one of the concepts early on in some of my development career as functional programming was getting a lot of attention was this idea of memoization, or the memento pattern of, I want to save the result of some expensive computation behind a thing that anytime I ask for the thing again, it already has it. So memoization, or this memento, task of T also kind of does that. I mean, it's a future that says, hey, once I have T, I'm always going to have it, and I will never recompute it again. The result property of task T, once it's done, is done. It doesn't change. So all the work that went behind creating that result is done. It doesn't need to be done again. And that's something that I wanted within the fork joint sample. I wanted to be able to say, once something is done, I don't need to do it again. So in the last episode, when we introduced the burger state machine, it really was saying, hey, if I ask for the same burger twice, don't give it to me, don't make it again. It's already made, just give it back to me. And that's where that requester came in, where it was like, hey, if you ask me again, I've already made it. Here's the burger you asked for. And it's saving that burger in the burger state machine. So when I was working on the code for episode 6, I really started to think, okay, well, now I need the order state machine. I need that orchestrator or that choreographer at the higher level so that I can fork out and create multiple burgers in an order. Because, you're going to order more than one. And so when I started to look at that code, it started to feel like cut and paste. It was just like, okay, so I have a state machine and I'm going to send a request. And I started looking at the existing primitives within MassTransit. And I said, okay, what's available to me is great and it works for this, but I need some additional capabilities on top of this. And the whole time I'm thinking, how can I do essentially async and await with messaging? Because, I mean, messaging has huge advantages. Unlike RPC with a simple HTTP client, excuse me, I have durability. I can relate to a durable queue, and I can guarantee that that order will be completed. Now, barring any failures, of course, and if failures happen, I can propagate those as needed. But I really want to be able to execute, and I want to submit that order and get the order back. And I want my application to be idempotent. If somehow I get a replay and get that submit order twice, I don't want to create two separate orders for that. I just want to say, hey, yes, that order is being created. Thank you for telling me again. I will let you know when it's done. And if you remember, we talked about the comparison is with the request response. Let's see here. Yep, task T is like lazy T. Yes, it is. I mean, it's similar in a way. Once it's resolved, it's done. So when we first started in the initial episodes talking about how messaging is different but the same, HTTP client doing an await post async is sending a message over the HTTP transport. It's transferring that message to the server's processing it, and then transferring a response back. And with messaging, we're sending that request. It's being consumed from the queue by the consumer. A response is being sent to another queue, and that response is being picked up. And in MassTransit, the request client has things like timeouts. You can say, hey, if I don't get a response in 30 seconds, I'm going to have a timeout exception, and I can deal with that. But really, that's only there to deal with the unlikely and the unpredictable. It's like, and it's really a relic of HTTP. It's like, okay, I'm going to set my timeout of 30 seconds, and if the server doesn't reply, I'm going to disconnect, and I'll try again later. It's this fail fast mentality of don't leave an HTTP connection waiting on a response for 30 minutes because it's an unreliable transport, TCP could break, anything could happen. We have the durability of messaging. I've sent the order. I've submitted the order. I know it will be processed. So the idea of a timeout doesn't really matter. I know that there should be like a deadline where if the order isn't here in 10 minutes, the person's going to walk out and I'm going to have to refund them. But that's a compensating action. That's something I'm doing because the system didn't do what it needed to do. The grill guy was on break. You didn't tell anybody. Burgers were never made. Customer walked out the door. I deal with that a different way. I refund the customer's money. The order doesn't go away. It was still ordered. It's just it might be canceled. Or if pieces on it weren't there, they'll reshelve those and give them to somebody else in the drive-thru because that's how they do it. It isn't going to take that order away. And so when I think about the burger state machine and how that fits in, and I put a diagram of that, I introduced this mental model of this idea of a durable future. The fact that it's a state machine is irrelevant. That's plumbing, that's under the covers. I have a durable future. And with a durable future, I can compose my system of things that may have already completed, but I can always ask for them again. And if I think about that at the highest level, when I call create burger with the same ID and dressing, condiments and size and everything each time, if that burger is already created, the burger state machine immediately returns that burger back. And we can see that at the bottom. If I order the same burger with the same identifiers, it says, yeah, I already created that. That task has completed. That durable future, it's durable. I've stored the state and I can return it to you at any time. And I can do that over a standard request response model. I don't have to think about, oh, well, I need to go and query this or do that or whatever. I could just ask for it again, and I know that if it's already been done, I will get it. And that's an enabler a lot like async and await. If I've already awaited a task, I know the task is completed, I can pass that completed task to anything that requires an async method, or accepts, I should say, an async method, or an async argument. And it will either wait on it if it hasn't completed, so everybody can wait, everything can back up behind the thing that isn't done, or it can say, yeah, I've already done that for you, and here it is. And there's also the concept of if I ask for it multiple times, let's say it takes 3 minutes to cook a burger, 12 minutes to cook a steak, who knows? 12 minutes in a steak in Texas is probably against the law, although I see some well-done steaks coming out. When that first request comes out to order the burger, if it's going to take 3 minutes to cook, and if I time out at 30 seconds and ask for it to be created again, it's going to say in that concurrent request, that second box here, I'm already creating it, but I know who you are and I'll let you know when it's ready. And it will then, if they're still waiting for it, they'll get it. If they aren't waiting for it, the response goes away and whatever, they'll get it next time. So this concept of a durable future is something I tried to explore in the code base. And it took me a couple days to grind through this. I worked on it last night kind of extensively to kind of see how it works. And I'm glad I did because it kind of let me refactor the code a little bit. And I did it in 2 steps. And episode 6's code will be 2 commits. One will be just the changes. And then the other one will be where I added Entity Framework Core with SQL Server in a Docker container so that I can actually show the interaction of how this works in a durable state. With the first commit, it's just all in memory. Totally fine. Perfect for testing. Super fast. Yeah. So I want to go back into the code now and look at that burger state machine. Because it's still called the burger state machine, if I can spell it right. State machine. Okay, so the burger state machine, we have the same 3 events. A burger was requested, a burger was completed, or burger faulted. And if we remember those events, because our burger is created with a routing slip, the 2 events for the burger being completed or faulted are a routing slip completed or a routing slip faulted. The initiating message, order burger, is that request type that would come from the request client. Now I've put some plumbing down here for things like creating the burger completed message or creating the burger faulted. In previous examples, it was called burger not completed, but that seemed kind of contrary to the model of going with a durable future. The durable future can either be completed, it can be faulted, or, and at some point I'll add this, it can be canceled. Although cancellation is kind of a weird thing. It's like, usually when you call something that requires a task and it takes a cancellation token, sometimes that's actually a cancellation token, and a lot of times it's just a timeout. It's like, hey, if you haven't made it by this time, forget it. I don't need it. I'm already going to hang up. Or like if the HTTP connection is dropped from a client on an HTTP request, it'll set the cancellation token, giving you the chance to either back out or just stop consuming resources because the caller's gone. So I switched the terminology to completed or faulted so that I was consistent with that model of task of T. And I can format the message any way I want to, but the states within the state machine are completed, faulted, or waiting for completion. just like a task of T, which is, again, that future that's happening within the .NET framework. This kind of dried up my code a little bit because I created and introduced so if we look at burger state has really narrowed down. Burger state has an order ID. It has the burger, which is the actual result of the task. It has the tracking number of the currently executing routing slip. And then it's derived from this base called future state. Future state has the things that matter for the state machine, for the durable future. The fact that it's built with a state machine is just the plumbing. It's just how it works. It has the initiating response address and request ID, which I'll cover in a second. It has the time that it was created, and then the times that it was either completed or faulted. And then it has a correlation ID, which identifies it, because these all have to have some identifier. You know, when you're in memory, you have a reference. You basically have a pointer to the task of T object. Here we're using a GUID to keep track of it so that we can have a reference to that from any message that we're in. The burger state keeps track of the extra details. The exception info, maybe that belongs down in the future state. Like I said, this is a rough refactoring of what I did the other night, but it still works. So initially when that burger is requested, and again, let's go back to our diagram, if I can find it. Our durable future. When that first burger comes in, we're going to execute that routing slip and then notify that the burger completed. Now, originally, in the previous version of this, we were putting all of the response addresses into this separate request state machine, which tracks requests against a state machine. And while it was convenient, it didn't make sense, and it actually introduced an additional message delay for every completion. In fact, 2 extra message delays, because a message has to be sent to the request state machine, and then the request state machine was sending the response. And that's great for a concurrent response. If you think about it, when you await a task, it's actually adding a continuation onto that task of T that it then calls once the task is completed. And that's essentially what the request state machine is doing. And so I will probably rename this with some new plumbing at some point when I get on, or add a new one that fits the future model better. But it's what I'm using for now to keep track of subsequent requests that are presented to the future when it hasn't completed yet, so that they can all be continued or notified so that they can continue executing when the durable future completes. So it's just keeping it out of band. I thought about putting all of the subscriptions or continuations into the actual future state, but that means that every time there's a new subscriber, I'm mutating the data that's in that state machine. So I kind of wanted to avoid that. So that's kind of where we are. And I'm thinking about this in terms of how I can limit the overhead on the system when it comes in. Any subsequent request, once it's completed, immediately respond and reply from the future state. So if I'm completed or faulted and they request the burger, I immediately return the response that's already been saved. You know, whether it was faulted or completed, I have it. I don't have to go anywhere else, and it's immediate response. Yeah. And since there's no changes to the entity framework core just releases the transaction and no commits are necessary and everything's great. That was kind of a jump ahead, but. So to do this, I put a couple additional extension methods in here. So like anytime this is active, when the burger is completed, I'm going to complete the burger. And completing the burger is just, in this case, pulling the burger out of the routing slip variable. So we're basically task completion source dot set result. I'm setting the result of my durable future. I'm then creating the burger completed message using set completed with that burger completed. Now this is a future extension which does a few things. First, it sets the completed timestamp. It then checks to see if we have a valid request ID for a subscription, the first initiating subscription within the future state. And if so, it's sending that response to it. So this is basically what respond async does, but because I've kept the values separately, I'm just responding to it with the request ID by doing a send to that response address in the state machine that I've captured. And then I'm calling request completed, which notifies the request state machine that this future is done, notify any subscribers that have connected to this future and want to know when it's completed that they have done, that their responses are there. So any other requests that have come in, those responses will be sent by the request state machine, which is separate. And yeah, I don't want to go into too much super detail on that, but we did that last time. So that's the set completed. And at that point, I transition to the completed state. Now I could probably roll this into like a single method. Again, this was just my first pass at kind of cranking these extension methods out. But I'm creating that burger completed or burger faulted message that's going to be used in the higher level order state machine. So previously, the consumers were doing all of that, and we had jettisoned the response consumer and things of that nature. So now we're going to actually look at the order state machine that has been added in this release. So episode 6 is taking this future state that's been kind of teased out of the burger state machine and brought to the next level higher. And this is where the fork comes in. So the fork in its food, obviously. Yeah. So before we completely jump in there, I want to bring up Postman and look at what we're posting to the HTTP endpoint. So I've modified the controller a bit because I want to start at the very beginning now that we've seen how the burger has been adapted. So my supported post that I can put in here now, you can see that I've changed burgers to be a collection or an array of maps where each one has a burger ID. Each one has its own definitions, whether it has lettuce, cheese, pickles, onions, ketchup, mustard, and the weight. And I've modified the grill so it takes a little longer to cook the pound burger than it does to cook a quarter-pound burger. So, you know, physics are coming in here a little bit. It's getting fancy. Actually, I just didn't want them all to complete at once because it's kind of boring. So I'm just going to send this in. And before I do that, I'm going to actually have to run this. So again, we're running it local. I've set it up so that all the connection strings and everything are adjusting depending upon whether it's running in the container or not. So if it's running with SQL Server up and running, it should just go. We're going to close Swagger because we're using Postman now. And I'm going to send this multiple item order to the service. And we can see that my order state machine is running. All 3 burgers are being grilled concurrently. They're going to complete independently. They're going to finish up their work. And at some point, once they're all done, I'm going to get a 200 OK for my request. And boom, there is my order ID when it was created and completed, because right now I've still kind of kept in the output model those timestamps of the futures, because even the order is a future. And I've kept the order ID, the burger IDs, everything that was completed and done is there. And so I have to hard code this because I haven't found a way to like take parameters out of an output and replace the GUIDs. But I'm going to put the GUIDs of the different items I created. And I'm doing this by hand, so I don't have a script because it changes each time. I guess if I was smart, I would have done one beforehand and created another Postman item, but I'm not that smart. I don't think that far ahead. But I'm just copying the GUIDs, which identify the burgers that I ordered. Because Postman creates them, but it doesn't save them. So I guess maybe there's like a request body I could save. I'm not an expert with Postman. I've been using it for a whole week now, the new version. But now I went in and I put those GUIDs. So I'm asking, this is basically me submitting the exact same order I just submitted again. And when I send it, I get an immediate response. Because the order state machine the order is now in a durable future. And that future has already completed. I know the status of that order, and it immediately returns with the exact same information. And I even put a cute description that says, you know, this burger was a half-pound cheese, pickle, onion, ketchup, mustard, so that I would know that it was the burger I ordered. So yeah. So now, I mean, I can submit that order as many times as I want, and that request is going to complete every time. And I feel like this is pretty useful because I can stick to the standard request response semantics at some point in my application. And I don't have to say, oh, well, I need to use the get verb, or I need to use the change to another way to ask for it, or I need to go ask for each item. I don't have to think of a bunch of different ways to approach the problem. At the top level, I need this order. Is it done? And that's the future, and the future has already completed. So yes, it's done. And here it is again. Same as I told you last time, but great, it doesn't matter. It isn't, I mean, you could call it a cache, but it isn't cached because it's completed. This isn't a cache. This isn't like loading some state into, you know, an edge service like Redis or Elasticsearch and saying, oh, what was the last state of my order? This is the order. This is the completed future. And I'm able to just immediately request it and immediately get the response back. And to me, that's pretty cool, because now I've started an order and I have a burger, but when I add a drink, when I add fries, when I add the other things, when I add dependencies on the burger that are dependent upon subsequent durable futures down in the tree, what's the phrase? Turtles all the way down? You know, async all the way down. Once you go async, you got to go async all the way, because you can't go sync, async, sync, async, sync, async. But if I'm able to give myself completable futures that I can just request response, I don't need timeouts. I can just ask again later. I don't have to worry about implementing timeouts all the way down the chain. I can deal with those behind the durable future without thinking about it. You know, the order is just doing requests to burger state machines. The burger state machine is executing routing slips. They're both completing in different ways. When I add or drink, I can do that as just a regular consumer. I don't even have to write a routing slip or a state machine for it. I can just say, hey, here it is. Now, a consumer doesn't have state, so I still would need to use a future state, but I could just have a simple method that does that through a consumer instead of using a routing slip. So I think this is a pretty cool paradigm, and I think it unlocks some pretty slick capabilities. And you know, I'm trying not to be blown away by it mentally, but when I've talked through it, and I talked to Drew about this last night for a couple hours, and he started bringing up the way some other languages are trying to pull these idioms into their platforms, and the durability is lacking. They're all, you know, we have futures in Rust, yeah, but they aren't durable. You can't depend on them out of process. You know, there's people that have tried to build solutions around this, and when I came to thinking about it this way, I don't want to say it was novel, but it seemed like, again, these are all just underlying components that I'm using in a way that makes more sense. And I think it resonates well with developers, because they can think of something as like, have you done this? Oh, you did? Great, thanks. If they ask them again, these are computers. They don't get mad. They don't care if you keep asking the same question. So I think it's kind of a cool model. I'm going to jump into the order state machine to show how it's different, because we've just looked at kind of the output of it. So how do I do this? So it looks almost exactly like the burger state machine. It has a initially, when the order is submitted, it initializes the future, which sets the create timestamp. It says, hey, if I have burgers to order, I'm going to get the number of lines. So orders and lines go together. An order has lines. That's just the way supply chain talk works. It isn't items, despite what some people try to do. It's orders and lines. That's basically how orders work. If your terminology is different, map to mine, because that's how my brain thinks. So when the burgers come in, I keep track of the number of lines. I initialize the line count. I don't use it for anything, but it's great to have. I then take my existing pending line collection that's part of my future, and I union in all those burgers. So I say, hey, all those burgers, get in there. These are all things that have to happen. These are my pending completions that I'm waiting on as part of the order state machine. Yeah. Then I created a new activity called request burger activity. I need to change it to create burger, because I renamed the request burger contract to create burger. Hey, Brave Cobra, I forget your real name, but welcome back. Awesome to have you. Oh, blue. Yes, barn full of owls. That's funny. So the request burger activity is then now going to be, so previously we were using the request client to create the burger. Now we're just saying, hey, for all the burgers that I have, do the thing that I absolutely recommend nobody does, but I did it this way anyway. Don't await this. I should fix this while I'm sitting here, because I feel like a tool, but this is the slowest way to publish messages in MassTransit, is to await publish each time. I should have done something like context.data.burgers.select x, then let's see here, consume context.publish order burger. I should take my new that's right here. Yeah, I did this the absolute worst way possible. I feel really bad about it. X, let's just rename that to burger. Yeah, await task.whenAll. Okay. That should do it. Okay, that makes me feel a little better. I'll get rid of that. But yeah, so that's the fastest way to publish in MassTransit because it's going to actually buffer all those up and send them as a single batch. Yeah, so do that. Don't do this thing. It's bad. This is slow. I'll just put a comment on here. This is slow. I'll take that out before I commit it. It's just funny. It's like, don't do that. Do this. Because it'll do them all parallel, and then MassTransit will batch those up as a single batch to RabbitMQ, which honestly, it saves 10 to 15%, but this right here waits for each message to be acknowledged by the broker, which if you have a 3-node HA cluster, can take, if you have really slow storage, this can take tens of milliseconds, which is really slow, which means you could only publish like 100 messages a second. Yeah, I'll leave it in there and say, this is slow, don't do this. Good point, yeah. Also, make sure you always call next.execute because I spent 40 minutes trying to figure out why I wasn't getting past the initial state, only to find out I left this line out. Activities in a state machine are a pipeline. It's kind of like railway programming. You roll down the execute track until an exception is thrown, and then you switch to the faulted track. And so faulted can then correct and jump you back on the execute track. But again, anytime you're in a pipeline or a railway model, in this case, it's a railway model, and you have to execute forward until you jump the track to faulted. And the infrastructure handles the track jumps for you. So you don't have to do it. Just always call await next, and everything will be great. If you throw an exception, don't, obviously, because that's when the track jumping happens, but you know what I mean. Question in the chat is, what is union with? Union with is a feature. Okay, so let me jump into the state so that we can show how the order state is tracked, because I think that'll help answer some questions. So again, I'm using that same future state base. I put an updated in here, but I don't actually use it yet. I have the line count, and then I have 3 collections. I have a hash set of GUID, which is all of those lines that are pending. And so union with just says, hey, here's an enumerable of GUID. Make sure that these are all in this hash set. So if the hash set was empty, it just puts them all in there. If the hash set had some of them already, it just makes sure that they're all in there. No big deal. It only happens on the first call to create burger because the order shouldn't change. Same ID. And then I have 2 dictionaries, each keyed off GUID based on completed or faulted. So this is the join of the fork. So the initial activity that kicked off all the create burger commands, that was the fork. That was like the whole point of being called fork joint. The dictionary here is the joint, thus the second half of joint. And as those responses come in, we can see when we look down in here, the events we're looking for are order line completed or order line faulted. And this doesn't have anything to do with a burger, but as you might imagine, I did the thing that makes sense to do when you do this, is I have an order line completed interface that is then implemented by the burger completed event. And that has the details like what's the order line ID, what's the order ID. And this is where the description for the burger comes in so that I can print it out on that tray sheet that says, here's all the crap you should have in your order before you ship it. It also makes it legible, so it's like, hey, you can physically match with it. And it also makes it easier to test and make sure it's showing up. So the order line completed, the other one, and that goes back to future completed, which again, just has the created and completed timestamps. And that way, once I add fries, drinks, whatever to this, they're all just lines. It's really just a matter of the request burger activity and creating activities to actually fan out and do the fork to go off and send the other requests. Now, these aren't requests in the state machine because I don't care about timeouts, and I don't really care about the types that come back. I mean, I do because I have events for them, but I'm just telling them the response address in this request burger activity is actually my input address for my durable future, my state machine. Because I want the response to come back. And if that burger's already been created, it immediately sends a message back that says, hey, you're already created. And if this durable future has already completed, it doesn't even go anywhere. It just says, hey, I've already completed. I can respond immediately with create order completed, which simply just maps the lines completed to the response order completed. It's just taking the collection of data that it already has and sending it back. For the case of order faulted, I'm not passing the exception right now because there isn't an order exception yet, but each of the lines faulted, which if we remember in here, is an order line faulted, which has the future faulted, which has created faulted, and the exception info that I get back. So if I go over to Postman, and I don't think this is running right now, if I go over to Postman now, and I undo my changes here, and let's say I ask for a burger with lettuce. I'm going to make this full width just so I can see it. Okay, so if I ask for a burger with lettuce, which we all know we don't have lettuce, we just don't have it, and I run this, it's running and executing in here. All the debugger's doing its thing. I'm grilling up my patties. Looking good so far. What's going to happen? Oh, looks like something's going to go wrong. Let me go back over to Postman. And if I look at the response, I can see that I was created, but I was faulted. And the lines that were completed, yes, they do come, well, they don't come back concurrently to the state machine. They are serialized through a partitioner because they're partitioned by order ID. But they all come back concurrently. It's just the state machine can't consume them concurrently because it's going to be updating the state and it locks the record in the database. So it actually made me think, and that's a good question. I sent a message to Matt the other day, and I was like, hey, so what do you think about making it so state machines can consume batch of tea? And I was really hoping for the response to be, you really should not do that. But I got oh, that might work. I mean, I would have to code it to do it, but it's like if I could make a state machine receive a batch of line completed, I could seriously reduce the database overhead of a durable future. So that might happen. So good question. It's seriously possible that I might do that, but right now it doesn't work. You can't send batches. Each one is one at a time. But if I do come up with that, that'll be cool because then like if all of them complete immediately, I can get one batch at the state machine, do a single database transaction, update them all, and then it's like love. So that's what I'm thinking there. But yeah, for now it's basically just serializing. And if we look in the console, we can see that there's 3 in a row: saga, 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 used, used, used. It executed those statements individually. And if you looked under the covers, you'd see 3 EF core transactions to the database. But yeah, each one of those is currently received independently. In 2 cases, we received order line completed, and in 1 cases, we received order line faulted. Yeah, so good question. Back to Postman, we can see that we had 1 faulted line. And the reason is because they asked for lettuce and there was no lettuce available. And that's why that one faulted. And it will never change. It's that order will be faulted. So that's how the order state machine works. I have a couple other things I want to talk about specifically related to the lettuce, and I think these are going to be like future episodes, but I just kind of wanted to bring them up because there were questions that came up when I was talking about it and going through this originally. We're still using the itinerary planner that we had before, so that behavior of building the routing slip didn't change. In fact, the burger state machine, the only change made was to convert it to a durable future. I don't think there were other huge changes. The order state, like I said, it's keeping a hash set and a dictionary. And I store these, so let me go over the EF core part real quick, because I feel like that's worth taking 5 minutes to discuss. If it's 5, it might be 2. If I go to my startup, why do I even use the mouse? I'm a keyboard jockey. I want to kind of go over some of the things that I do differently in here, because this was introduced in MassTransit 7.1.2, I think. It might have been sooner, but I have this concept of, first of all, I have a single DB context for my 3 different state machines: order state, burger state, and request state. Request state I don't own, but I was able to map it. It's in the MassTransit library, but it isn't part of my code base. But I added that single DB context with use SQL Server connection string. And I do some mangling in the connection string to say, hey, if I'm running in a container, change localhost to MSSQL, because my Docker Compose has SQL Server registered as MSSQL. Right. So that's the question I'm going to cover after I go through this. So hang with me there. I'll bring that up in a second of like how to deal with lettuce, how it really happens in the real world. Because we know in the real world, the dress guy says, hey, we ain't got any lettuce. And the person waiting in line says, that's fine, I'm hungry, feed me. And they just ship it without lettuce and they're fine. So I'm going to talk about that because in supply chain, that's a huge part of the business called substitutions. It's like, hey, you can ask for this, but you know what? We got these other gloves that they cost us 10 cents more, but we charge you twice as much, so we'll give you those instead. I'm not talking about my company. I'm saying some unscrupulous company might do that. But they're going to give you, they'll typically up convert your order with a substitution if the demand is high and it looks like, hey, this is what you need for fulfillment. Because nobody wants to come back the next day when they're in stock and get the item they wanted and deal with all the shipping. Sometimes it's easier just to throw a comparable or compatible product that isn't a downgrade to the customer instead as a replacement. And it's called an item substitution policy or a line substitution policy. So that's pretty common in supply chain, and that was one thing I was going to talk about. I guess I just did. But I want to go back to the startup. So we have the add DB context that has the 3 different Saga maps in it. We created our custom transit configuration before. The MassTransit scheduler, I'm using the RabbitMQ scheduler for this, and I'll show you why. This is the new syntax that I've put in here. And there's a new feature called Set Entity Framework Saga Repository Provider. They exist for all the repositories, but some of them are totally broken right now. Like MongoDB is just a pain in the ass, and I didn't code it right, so I screwed that one up. There's a couple that don't work because they require the iSaga version. I think Redis is another one. But if they don't, and they are basic like EF Core and Hibernate, Dapper, Cosmos, table storage, they all just work this way. And you can define the Saga repository once and say, hey, anytime a Saga is registered that doesn't get explicitly registered, use this to build their Saga repository. And you have to register them with the type of syntax. Because if you go into the whole point is if I try to do a continuation on this, there isn't any. It returns like nothing. It's void. So I can't configure a Saga repository for these types because I don't have the generic types. So by using the type of, and this is, if I just said add Saga state machines from namespace containing, it would also work because it just goes and discovers them. But the whole point is this will allow you to register the Saga state machines by type and use the previously registered Saga repository provider. And so it will just take the generic type off and just pull these things in to use that existing DB context. So it sort of simplifies configuration. I had some weirdness with the Mongo thing that I couldn't figure out, and then I switched to EF. I was going to try to use Mongo, but again, Mongo just fails me every time I try to use it, so why bother? So I switched back to EF Core, made total sense, worked the first time, and everything was great. So that's how I've configured EF Core in here. For each of these different sagas, I've defined a couple of things. Since I've started this effort in this sample, I've really tried to keep RabbitMQ really clean. I'm trying to limit the consumers, the queues that I have in place. I'm trying to really keep the exchanges down to the minimal set possible. I keep looking at them, finding things I don't like. And you'll notice that there aren't a lot of types shown in here. Like I have order burger, like request burger is no longer used. I can delete that exchange because it's no longer a type in the system. But submit order burger, I've continually kind of deleted these because I don't want the extra stuff in there. And you'll notice there's no like order line completed or burger completed or any of those. So, and the reason for that is I'm telling it not to bind those types because I'm giving them the response address to send to. I don't want to be tied into a publish of a line completed. I don't want that information. So in this case with RabbitMQ, I'm saying, hey, don't configure this automatically. The only message I want you to send me is submit order. And it will still consume other types sent to it. It just isn't going to set up RabbitMQ to do it for me. I'm also giving myself a partition count, setting up a partition on the 3 different message types I support on this endpoint. In fact, I think, yeah, that's good. And then for use scheduled, and then I'm setting up scheduled redelivery because this is the kind of retry where I really don't want to hold the message on the queue. So I'm telling it to send it back to myself in a second. I originally had these intervals bigger, but I made them smaller for testing because otherwise I just see the error spew down millions of times. But because I'm using a database, I have to have some sort of retry capability because concurrency issues might happen. I'm using the partitioner, so they shouldn't, but they can happen across instances in a cluster, so something to keep in mind. And then I'm using the outbox to ensure I'm not double sending messages. And I've accounted for that in the actual state machines. If we look at the order state machine, if I get, so during any, even if I've already said I've completed, whenever I get a line completed, I will complete the line and then complete the order if it's ready. Because if I receive the same message when I'm already in a state where I should be done, it means that I might have had an outbox conflict and I want to go ahead and reproduce those messages. Yeah, the other piece of this is there's the order state map, and this is the EF core map. So the EF core map, I have current state, created, updated, completed, faulted, line count. I have the request ID and the response address of that initiating requester. So again, just like we did in the state machine with the order, and I tried to redo this last night to make it show an overlapping submission better, but I'm not sure I finished it. So, but you submit the order, another order can come in, and that's when it does a request started because it only has room to store one response address. So anything over one, this was an optimization to not make them all go to the request state machine. So it'll send that subsequent request to the request state machine, and then it will loop through all the burgers, order burger, burger completed. Once all of those are done, it sends the order completed to the initiate, this guy, and then it sends the request completed to the request state machine, which is then going to send the order completed to this guy. So I didn't finish this last night, I guess, so I'll just clean this up once it's done. And then again, once the order has been, once the durable future is transitioned to completed, it's an immediate response with that order. I do some tricks in here using a JSON value converter. Matt put this together for us, and it's basically taking that hash set and serializing it as JSON. I actually had to pull these types into my local project because what I found out is this JSON helper wasn't using the MassTransit serializer settings, so it wasn't working with interfaces. So once I put these settings in here and copied these types into my local project, I was able to get that working to where it serializes without the types. So this is where I'm going to show one more thing, if I can, a project that, where'd it go? Oh, fun. I'll see if it works. So Albert mentioned this project the other day, and so I thought, heck, I'll give it a try. It's called DataGrip. Apparently it lets you talk to databases, but it'll actually let me talk to my database in my container. So if I go to my tables and I look at my order state, I think I can just do select star from order state, and I can see that I have my correlation ID. A lot of these are in the completed state. A couple are in faulted. I have my response addresses. I have, and you can tell when I run them in localhost versus in the container. It's kind of funny. You can see the request ID, the response address, the completed. And then if you actually look in the lines completed, lines faulted, you can see the actual JSON is in there for the message that was received. So it keeps track of all those messages and just serializes them out to a varchar max, which I think the limit is like 2 gigs, so it should be fine. Yeah, so that lets me actually store the data so that I can generate that response message anytime I want to. Yeah, so that's pretty cool. That's a neat little app called DataGrip. Another JetBrains product, but pretty slick. So that's how I'm handling that within the map. And I do that for both the lines completed, the lines faulted, and the lines pending. And I just adjust those in response to the messages. So that was the thing on that. The comment about substitutions. You know, substitutions are kind of a key thing. They're usually handled by the fulfillment side of the business. They don't usually change the order. They may update inventory because obviously you're pulling a different inventory item. And if inventory thought you had something and you didn't, that's another inventory check. And you might do just a quick count or a quick inventory on that item and do an inventory update. But substitutions would typically happen downstream. And the question was, you know, if the future is already faulted, it can never become completed, and that's correct. And in that case, if I was doing an automatic item sub thing, I may not complete, that future may not complete until the product is picked, packed, or shipped. So again, it depends how far you want to pull the order management system down into the supply chain. like I said, in the burger restaurant, they're like, hey, the lettuce is bad. You okay without lettuce? And the person is like, fine, just do it. Nobody cares. There really isn't an inventory checkpoint because you didn't have lettuce. It's something you just didn't deliver and the customer was fine with it. It isn't something you charge extra for. If it was something you charged extra for, you might be like, hey, you want jalapenos instead? And be like, hey, sure. A handful of jalapenos isn't going to make or break a restaurant when it's a matter of getting a customer out the door. So substitutions you could handle a number of different ways. I think it just depends what part of the business you're building. But the durable future, once it's completed, it can't change. And I don't think you would necessarily change the order and say add a line to it, because again, you're changing an order that's already an item. If anything, you would submit either a corrected order or you would submit a no charge packing slip to the warehouse. I mean, there's a number of ways you would handle it in the real world in the business. In reality, you might just run in the back and grab one and then just make a note to remove it from inventory and put your manager signatures and call it done. It all just depends on how your customer sat policy is for delivering those types of things. We talked about cancellations. I haven't put cancellations in here yet, but I think those will be coming because I think it makes sense. Usually cancellation is time-based, but it would also be like, okay, well, they want to cancel the order, so anything unfulfilled, roll that back. In the case of a burger, we might just put it back on the shelf and pitch it at the next drive-through item. There is a concept of doing a query only, just saying, hey, I don't want to submit the order again, but I want to get the current state. So potentially a query only, because state machines do support query only so that they don't lock the data. I'm just looking through my list of like possible to-dos to see if any questions come up. The transforming of the responses, that's all handled within the state machine code of the order state machine. And you can see where it's down here where it's like, hey, I want to create the different output messages. Those are just right there. They use the message initializers. Yeah, so I think it's a pretty empowering concept. Obviously, some of the next episodes are going to be around adding an additional food items to show multiple types of fulfillment of the fries, the fries future, the drink future, the shake machine that never works shake future. But this is kind of like, I don't know, this is the episode where Baby Yoda does something that changes the course of the remainder of the series. I think this introduces, some of the key, a key atom or a key new idiom within how applications could be built to this type of workflow. And it builds on the existing request response. So I'd be curious to see what you think. I mean, if there, leave some comments or hit the Discord channel. If you're watching this on YouTube, like and subscribe, whatever. But definitely subscriptions help on YouTube. It's a big thing. But I'm trying, as building this out, I see this as something that could definitely change the way I think about building asynchronous systems, of being able to just re-request something at a high level and get it resolved rather quickly because the future is done. So yeah, definitely, pipe up with what you think, leave some comments, because once this resonated, it was like, okay, so building out the rest of the menu is really going to be pretty easy with this kind of capability installed. So thanks for joining. Nice midday, midweek. This was my lunch, so it's back to work as of Monday, and it's been a hellacious work week, not to mention the craziness that's happened, in the recent day, but like the last year, but 2021's off to a great start. So yeah, definitely leave some feedback. I'm curious to hear what you think. Thanks for joining midday. I hope this was a good time slot. I know it worked well last week, so I want to try to hit it again. I'll get the code up on GitHub soon, and thanks for joining.